Okay, so last time we talked about the fact that octahedral metal complexes have splitting of the d orbitals like this, where you have 3 lower energy orbitals that have T2G symmetry and 2 higher energy orbitals that have EG symmetry. And the splitting between these orbitals, or the difference in that energy for octahedral complexes, is delta O. So today I want to talk about other geometries, but let me just review. So we talked about last time that delta can depend on a couple things. So delta depends on the metal ion, so the actual identity of the metal ion, which is related to its size. So if you have an increase in size of the metal ion, you have an increase in delta. The charge on the metal ion also affects delta. So as metal ion charge increases, the delta increases. And both of these, if you increase size or increase charge, what you end up doing is increasing the interaction between the ligand orbitals and the d orbitals on the metal ion. So you increase that interaction and you make the difference in the EG and the T2G set larger. And the last thing that we talked about was the type of ligand and how that affected delta. And this was the spectrochemical series. So all of these things we talked about in the context of octahedral complexes, and today I'm going to talk about other types of complexes, or I'm going to show you how the geometry of the ligands will affect delta. And then after we talk about that, we're going to get into how that delta affects the spectroscopic properties. So again, last time we only talked about octahedral geometries, and now we're going to talk about some new geometries. And I'm going to cheat, and I'm just going to represent octahedral as OH, even though some of my octahedral metal complexes might not be in the octahedral point group. So I'm just using that to represent octahedral geometry. So octahedron, or octahedral geometry, is one of the most common types. Another very common geometry that we'll see is tetrahedrons, or the tetrahedral geometry. And I want you to refer to figure 20.9 in your textbook, because this shows you how the metal d orbitals interact with ligands in a tetrahedron. If I define my x, y, and z axes like so, where my z axis is up, you can draw a tetrahedron by drawing a cube. So if my metal is in the center of this cube, the tetrahedron ligands are pointing to opposite corners on the top face and opposite corners on the bottom face, like so. And so you could represent this as the ones in the back 2 corners are going back, and the one on the front 2 corners are coming out. So that's how I'm going to define my axes for this tetrahedron. Now, what it turns out to be is that depending on which orbital you have, so the xy, so dxy, dxz, and dyz, they all point at edges of this cube, whereas the dx squared minus y squared and the dz squared all point at the centers of the faces of the cube. And you'll have to look at the picture in figure 20.9, or you can come into my office and look at the d orbitals. It's kind of hard to see in a drawing, but the ones that are pointing to the edges are actually, the orbitals are actually closer to the ligands than the ones that point at the faces of the cube. And so what that ends up giving us is a different type of splitting, where if I draw my d orbitals, now I'm going to split them in all of the ones that are pointing at the edges are going to be closer to the ligand and have more interaction, and so those will be a higher energy set. So the 3 that are higher energy are the x, y, x, z, and y, z orbitals. And the other 2 interact less with the ligands, and those 2 are z squared and x squared minus y squared. And so basically here we have an upside down octahedral splitting. So if I look back up here at my octahedral splitting, I had the opposite case where 2 of the orbitals were of higher energy and 3 were lower. When I label these orbitals, my high energy set is going to be triply degenerate. It is a T, and it is T2, but not T2G. It's only T2. And the lower energy set is E. You don't use the G subscript or a U subscript either because there's no center of inversion in a tetrahedron. So you only use G and U when there's a center of inversion or a center of symmetry. And now we have a different delta here. This one is represented as delta T for tetrahedron. The splitting in a tetrahedron is always much less than the splitting you will observe for an octahedral complex. So a delta T will always have a smaller difference in the energies than a delta O. In fact, if you're comparing 2 metals with the same types of ligands, yet one is forced to be in a tetrahedron and the other one is an octahedron, you will find that delta T is equal to about 4/9. So just less than a half of the octahedral splitting. So anytime you have a tetrahedron, you will always have a smaller energy gap. Tetrahedrons are always high spin, so you always fill in all of the orbitals, even the higher energy set, before you start pairing electrons. Yes, because the difference in this delta T is less than the pairing energy. Okay, so depending on the geometry you have, you know something about what that delta is going to look like. Now I want to go back to kind of an octahedral geometry, and I want to talk about how other geometries arise from the octahedron starting point. So we can get even more geometries starting from an octahedron. And those geometries arise in order to optimize ligand field stabilization energy. And this is always, so ligand field stabilization energy is an important thing that causes metal ions to prefer certain geometries based on the number of d-electrons that they have in the metal ion. So this is really based on the number of metal d-electrons. And this is why it's really going to be useful to you to be able to recognize what the d-electron count is in a metal complex. Because it basically determines what your properties are going to look like. So first, let's talk a little bit more, before we go into other geometries, let's talk a little bit more about ligand field stabilization energy. And I'm going to reproduce figure 20.7 in your textbook. So you can look at that figure later if you would like. I'm going to draw 2 axes here. And along the x-axis is going to be the charge of a nucleus, or you could also call it the charge to radius ratio, which is charge density. It's how much outer electrons are going to feel that positive charge of the nucleus, really. And if I go across from calcium to zinc, so the 3rd row of the periodic table, I'm going to talk about my metal +2 ions. And on the y-axis, I'm going to have the stability of just a metal hexaaqua, so 6 waters down to the metal. And so this is going to be my 2+ ions. So I'm going to start over here at calcium. So those are my 4th row, or really the 1st row of the transition metals, including calcium. Now, I've also, on this x-axis, I have in these 10 different situations, this also kind of represents the number of d-electrons on the y-axis, or in the x-axis. So as I go across, the number of d-electrons are increasing. Okay, so if we would guess based on the charge on the metal ion and the attraction that water is going to have for that positive ion, we might expect that there's a trend in metal ion stability or metal complex stability that's linear. So you would expect that as the charge in the nucleus increases, or as the charge density increases, you would have an increasing stability of the metal complex. However, that's not really what we get. So I'm going to label this as the expected trend. And this is based on electrostatic forces alone. The actual trend looks something like this. Calcium falls right on that line. Manganese falls right on that line. And zinc falls right on that line. But the other metal ions have a trend that looks like this. So this is my D0, D1, D2, D3 reaches a maximum, D4 comes down a little bit, and then D5 is right on that line again. D6 increases, D7, D8 is almost at the maximum, but D9 is a little bit higher, and then D10 falls right back to that trend. So what we get here in the actual stabilities is a significant variation for certain d-electron counts. So we get significant variation from this expected trend for D1, D2, D3, D4, and D6, D7, D8, and D9. Why is this? The explanation comes from ligand field stabilization energy. Other way to say this is that only D0, D5, and D10 are as expected. Okay, so the only ones that are as expected are D0, D5, and D10, and it turns out that those are the ones that don't have any ligand field stabilization energy. Let me just remind you what ligand field stabilization energy is. The energy of stabilization that's gained by the crystal field or the ligand field splitting relative to the energy of the unsplit state. So I'm going to give you an example. If you have a D2 metal ion in an octahedral field. Now, I have been telling you that these degenerate orbitals are where you have no ligand field around, but it's not really fair to compare no ligands to a ligand split state. So what I'm going to tell you now is that this, you can think of it as no ligand field, but in reality, it really is like a spherical ligand field. And the actual no ligand field would probably be of lower energy. So this would actually be no ligand field. When you have ligands around, it raises the energy. And then if you consider the actual geometries of those ligands, then you get a split state. And we split the octahedron into 2 higher energy Eg orbitals and 3 lower energy T2G orbitals. So this is delta O. And you have the barycenter here, where the split from the barycenter to the Eg is 3/5 delta O, and the split from the barycenter to the T2G is 2/5 delta O. So if I have 2 electrons, because this is a D2 octahedral case, when I put those 2 electrons in the orbitals, I have lowered their energy. So this lowering of the energy is the stabilization that's gained by splitting the orbital energies. And again, we can calculate that using the formula where LFSE is equal to 2/5. And this is a delta O thing, so it's 2/5 delta O times the number in the T2G set minus 3/5 or 0.6 times delta O times the number of electrons in Eg. And in this case, that ligand field stabilization is just simply, it's 0.4 times 2. And there's no pairing energy, so you don't have to worry about that. So the ligand field stabilization energy is 0.8 delta O. So it all depends on how big that split is, really. So it's 0.8 delta O. Now, when a metal has any d electrons, you will end up getting a stabilization energy, except in the case of D5, D10. So D0, obviously, if you would have no electrons in this system, so if I erase those electrons, obviously you're not going to get any energy benefit from splitting those d orbitals. If you have any electrons, like a D1 or a D2, D3, D4, anything, you still have more electrons in the lower energy orbitals than you will have in the higher energy orbitals, and so usually you end up with some ligand field stabilization energy. The only case where you don't is when this shell is half full, and then you would have none because you'd have 3 down here and 2 up here, and that actually adds up down here to 0. And if you have 10, you have the same case. I'm going to erase this so that my notes represent what I wrote over here. So anytime you have d orbital or d electrons, any metal with d electrons will have LFSE except for D5 and D10. And obviously that includes D0 because it doesn't have any electrons. So geometries can shift even more to provide more ligand field stabilization energy. And I will give you an example of that. So the geometries can shift to provide even more ligand field stabilization energy than you would find in an octahedral case. And I'm going to use copper 2 as my example. Copper 2 is a D9. You remove the 2 electrons from the s orbital. I guarantee you, during your senior thing, if you have any metals in your project, Dr. Ocean or I will ask you about the d electron count. So make sure you can look at the periodic table and come up with a d electron count for any metal based on its charge and where it is in that periodic table. Practice. Okay, so if I have a D9 octahedral complex, I'm going to make my splitting big here because I'm going to show you something. So my D9, high spin and low spin is not relevant here because for high spin or low spin, or basically no matter what this delta is, you would have the same electron configuration. So let me just point out that that's not applicable. We can calculate the ligand field stabilization energy. It's going to be equal to 0.4 times 6 because there's 6 electrons in this T2G set, minus 0.6 times 3 because there's 3 in the higher energy set, and that is going to give you 0.7 delta O, minus a pairing energy. But again, here, you actually don't have to carry normally I tell you to just ignore the pairing energy, but in a case like this, where if you compared it to the degenerate case, so if I compare this to D9, where all of the orbitals are degenerate, we have the same number of paired electrons. So when the number of paired electrons in the split orbitals is the same as in degenerate orbitals, the pairing energy is completely irrelevant. So there's a real reason why you don't need to care about it in this case. But normally, you have to get it from actual spectroscopic data. Okay, now I can't do anything down here. So if I mess around with these T2G orbitals, make some of them higher, some of them lower, it's not really going to affect anything because they're full. But up here, if I split these orbital energy levels so that one was higher and the other was lower. So I'm just going to write my T2G here, pretend like they're all the same, because there's no energy benefit to splitting those T2G. But there is an energy benefit to splitting the EG orbitals. So here, I have changed, oops, I should have only one electron in that top orbital. Now I have altered my delta. I have kind of a new delta here. Basically, for the 2 electrons in this lower energy orbital, I've increased the stability of those 2 electrons. I've also decreased the stability for 1. But if you've increased for 2 and decreased for only 1 electron, your overall stability is increased. So what does this mean? This sort of thing, the splitting of the EG or the T2G set, will often occur. In this case, for D9 copper, you have a tetragonal distortion. So if you had an octahedral complex and you tetragonally distort that, basically the two ligands on the axes, on one of the two across from each other, are going to move apart. This is elongating along the z-axis. What this will do is decrease the ligand interaction with a certain set of orbitals. I'm going to decrease the ligand interaction with anything that's in the z-axis. And so those things are going to be the dz squared, the dxz, and the dyz. So what I do is I go from an octahedral set where I have z squared high energy, x squared minus y squared higher energy, and I have x, y, x, z, and y, z. I'm going to move this actually down a little bit so I can show the splitting. So if I split this, these two orbitals are going to split to a higher energy level and a lower energy. So this will be z squared is now lowered in energy. X squared minus y squared is relatively higher. And because I distorted the geometry, in order to optimize the top two orbitals, I also will disturb my bottom two orbitals, and so I will actually lower the energy of the xz and the yz, and the xy will be relatively higher in energy. And this is the orbital splitting that you observe for a tetragonally distorted or tetragonally elongated octahedron. This is also what we see for square plane. If you remove those two axial ligands completely, then you end up with a square plane. So a square plane is really just an extreme version of a tetragonal distortion of an octahedron. And it turns out that copper 2+ will always favor a distorted octahedron, and its preferred geometry is actually square planar. Sometimes there's axial ligands and sometimes there's not. So you would find this splitting in the D4H character table. So this goes basically from octahedral symmetry to D4H. And we already said, I just want to point out that D8 metals also prefer this. And that's because, so you saw for D9, you raise the energy of one electron, but for D8, you drop the energy of two of them, and you have an increased stability from just those two electrons. So what I just showed you is an example of something called the Jhan-Teller theory. And the Jhan-Teller theory says that configurations will arrange themselves so that two degenerate orbitals will never have two different electron configurations. So you can see that Jhan-Teller, so if I fill in my D9 electrons, these three in the bottom set are degenerate, but they all have the same electron configuration. These two on the top are degenerate. Degenerate just means they have the same energy. Okay? These two on the top are degenerate, but they have different electron configurations. And so Jhan-Teller theorem predicts that this geometry, octahedron, for a D9 complex is not stable, and it will rearrange. Jhan-Teller tells you when something will rearrange. It doesn't tell you what it will rearrange to. But anytime you have degenerate orbitals with two different electron configurations, you will get a distortion in the geometry.
What about for D8?
D8 distorts, but it's not because of Jhan-Teller. And I think I spelled Jhan-Teller wrong in the first. Yeah, I totally did. It's Teller. Okay, so Jhan-Teller theorem. Again, it says that configurations will arrange themselves so that no two degenerate orbitals have two different electron configurations. We know now that distortion really happens to optimize ligand field stabilization energy. just once again, Jhan-Teller predicts which geometries will be unstable based on this rule above, but it does not predict what the preferred geometry will be. You can guess, but a lot of the times there are two cases that would actually be fine just looking at the electron configuration, so you would actually have to do an experiment to see what the distorted geometry would look like. So, what Jhan-Teller tells us, just going to basically summarize every detail. So for octahedral complexes, remember the splitting, like this, you expect distortion for D1, D2. You would not expect it for D3, right? Because then you'd have all of these orbitals here with the same electron configuration. When you have low spin D4, D5, or D7, you will get distortion, but not for low spin D6. For high spin D4, D6, D7, and D9. So actually I should say high spin D4, D6, D7, and D9, because D9 is not high spin or low spin. For tetrahedral, remember that tetrahedral complexes are always high spin because they have a small delta. The splitting looks like this, where you have 3 on top, 2 on the bottom. Remember that the bottom is E, not EG, and the top is T2 rather than T2G. So remember, no subscripts, no G or U subscripts. For these, you expect distortions for, so D1, but not D2. D2 would fill the 2 lowest energy, and they would be degenerate and have the same. You would have a distortion for D3, D4, D6, D8, and D9. So Jhan-Teller is predicting what things are not necessarily stable in these geometries. Some of the distortions are more common than others. D9 is one of these really, really common distortions. So that's the example that I gave you above. D9 is almost always a distorted octahedron. It almost never exists as an octahedron. This D9 is your classic example of a Jhan-Teller distortion, and it happens quite frequently. Other things that we predict based on ligand field stabilization energy. And this is ligand field stabilization energy, not necessarily Jhan-Teller. Jhan-Teller optimizes ligand field stabilization energy, but on its own, ligand field stabilization energy will cause distortions as well. So D0, D5, and D10, we already said, these metals have no ligand field stabilization energy. That means they have no geometric preference, or at least they have no geometric preference based on ligand field stabilization energy. They could have a ligand field preference based on sterics, for example. D3 and D8 are found to strongly prefer octahedral to tetrahedral. So the emphasis is on strongly prefer. And if you look at their electron configurations, you would see why. In both of these cases, you have electrons in the low energy set. So if you look at D3, for example, compared to, the octahedral case compared to the tetrahedral case, octahedron would have more electrons in the low energy orbitals, whereas the tetrahedral would have 1 in the higher energy set. So the more you can put down here, the better. In fact, all metals, all other complexes prefer octahedral to tetrahedral based on the fact that the octahedral has a bigger delta and you have more orbitals that are lower of energy, so you can put more electrons down there and get a larger energy benefit. So there will always be some preference based on ligand field stabilization energy for any metal complex that has ligand field stabilization energy. And the Jhan-Teller distortion actually increases the preference for some electron configurations for something other than tetrahedral. And this is especially the case for D9 and also for D4, but mostly D9. Okay, so let's look at some electron configurations. I'm going to draw a lot of electron configurations across the page here. I'm going to draw my tetrahedral diagrams on top and my octahedral diagrams on the bottom, and I'm going to start with D0 metals. I'm going to draw very tiny electron configuration diagrams here. Tetrahedral and octahedral. So for D0, you obviously have nothing here. For D5, again, these are half full, so there's no ligand field stabilization energy. And for D10, again, you have no, you're completely full now, so you have no ligand field stabilization energy. So if you went through the calculation for D5 or D10, you should find that you get 0 ligand field stabilization energy. The result is that these guys have no geometric preference. Now I'm going to look at D3 and D8. So both D3 and D8 for octahedral complexes have no high spin versus low spin. They would be the same thing. You can see here that in the D8 case, you remember that this delta is bigger for octahedron. You have more electrons in the lower energy set. And so, this is D8, this is D3. In these two cases, your preferred geometry is going to be the octahedral because you have more of those electrons in the lower energy orbitals. For D4, low spin, or high spin, actually, let's just call it D4. So it doesn't matter right now what you do because either way you draw the electron configuration, you'll still see that there's a preferred there's a preferred geometry for octahedron. So if I put D4 like this, you still have, so notice here I drew the high spin case. In the low spin case, you would still have the same situation where you have more electrons in the lower energy set for D4. And so the preferred geometry for D4 is, if you compare these two, it's octahedron. But D4 will go through Jhan-Teller distortion because of the fact that the degenerate orbitals have different electron configurations. If I made this a high spin complex, you would still see that there should be a Jhan-Teller distortion based on this. And what will happen here is you'll drop the energy of 2 of the T2G and 1 of the EG, and you will end up getting an electron configuration to optimize the stability of that complex. So this is your preferred geometry, which is square plane or distorted octahedron. So the tetragonally distorted octahedron where it's elongated. And then D9 is the same way. So if I draw a D9 complex here, for D9 you don't have to worry about the high spin, low spin. For this case you have more electrons in the lower energy set, and remember that delta is bigger, so you have more of an energy benefit. However, this is going to go through Jhan-Teller distortion, and you will get, again, this Jhan-Teller distorted tetragonal elongation along the z-axis, or you will get in a more extreme case, which is a square plane. Okay, so I did D0, D5, D10, D3, D8, D4, D9. D2 is pretty self-explanatory, but I did skip over the fact that, so D8 here, we've already said a couple times that D8 will actually prefer a square planar geometry depending on what the ligands are. So here you can see that D8 would not actually go through Jhan-Teller, but it does distort. So D8 distorts because of ligand field stabilization energy. D8, especially with strong field ligands, and remember what strong field ligands do. They give you a large delta. These complexes will prefer square plane. So if we look at let's look at some platinum complex with 4 ligands. I'm going to draw the tetrahedral electron configuration for this. In the octahedral case, it's TD, OH. So in this case, we get a tetragonal distortion. It's only in order to optimize the electron configuration here. This is an interesting case because there are lots of things at play here. So keep in mind that if you look at these two geometries, this has a bond angle, the tetrahedron has a bond angle of 109.5 degrees, whereas the angle between the ligands here is 90. So the tetrahedron is actually preferred based on sterics. You obviously have no Jhan-Teller distortion, so based on Jhan-Teller, you would not expect distortion. What? Oh, thank you. Wait, 1, 2, 3, 6, 7, 8. So based on Jhan-Teller for the square plane, you would not expect distortion. But you would still expect that the octahedron would be preferred to the tetrahedron. So you'd have more. So as far as the LFSE goes, the octahedral is still bigger than the tetrahedral. So basically it's a balance of these things. And so only when delta is large, so in other words, when delta is greater than the pairing energy. Okay, yeah, when delta is large, you have a pairing, or the delta is bigger than pairing energy, and when you have the d8, this will distort into a square plane. And this happens, remember that delta is large. So delta is larger with strong field ligands. So it depends on the spectrochemical series here. D8, so for the square planar D8 is most common for 4D8 and 5D8 metals. So if you look at the D8, like just considering metal plus 2D8, palladium and platinum, which are in the 4 and 5D row, palladium and platinum are almost always square planar. But nickel really depends on whether you have a strong field ligand or not. So nickel will be tetrahedral with something that's weaker field. So 3D8 metals like nickel. When you have pi donor ligands, what do pi donor ligands do to delta? What do pi donor ligands do to delta? Where are those pi donor ligands on the spectrochemical series? They give you a smaller delta. So nickel already it's in that first row of the transition metals. Relative to palladium and platinum, it has a small delta. Now, when you put a pi donor ligand on there, you further decrease that delta. And so the nickel compounds with pi donor ligands are typically tetrahedral. And that's because there's a small delta. So most of the times you can just consider that any of the D8 metal ions would be square planar, except that nickel already has a small delta, and so it really does need more like of a pi accepting ligand to increase the delta so that you would have a square planar. Otherwise, nickel exists as a tetrahedron. So nickel with any 4 halogens, for example, would give you a tetrahedral nickel complex.